Back to this last chapter on external flow. And before we start the material on drag and lift, I want to pick up something that we discussed last class. We discussed the wing loading of birds. And I presented this plot, which is quite an old version, appeared in 1954, this book by von Karman. And I've put on Blackboard the link to the book on Google Books because you can actually read, I mean, it's a really short book from Dover Editions. And if you're interested, you can buy it. It's quite cheap. But if you want to just browse some pages, it's on Google Books. So you can have a look. It's really an interesting little book about the history, from the historical perspective. So anyway, we discussed this a little bit and how sort of historically these questions about theory of flight were asked and answered. And then we had a very good question from Yasmin at the break. What about the pterodactyls? Where do they fit in this idea that, there's a limit to living creatures being able to fly? And so thank you for your question, Yasmin. Of course, I went right back into Google. Google is your friend. And started looking this up without imagining it was going to be a time sink because, of course, I found so many interesting things about this. So the pterodactyls are, of course, a variety of the earliest vertebrates known to have evolved powered flight, but there's a variety of them in different sizes. The largest of them is the Quetzalcoatlus. How's that? I can pronounce that because, in fact, it comes from Quetzalcoatl. That is one of the Mexican gods, and I can pronounce that one from the language of the Aztecs, the Nahuatl. So this was the biggest one, and the wingspan is estimated to be about 10 meters. So what about this guy? How does it fit in that picture that we were talking about, wing loading fitting sort of in this scaling? And I found this result where, in fact, this largest one of them, the Quetzalcoatlus, Northropy, I guess that's the one from the north, with the one that appeared in Texas, the one that was first discovered, is here in this plot. Okay, so if you see around, this one is actually in metric units, this plot, and it has the wing loading against the body mass like the other one. And you can see that this guy was quite big, around 100 kilograms, so it is about the size of a human in terms of weight. But wing loading is, in fact, if you look at it, here are these pterodactyls, and here are the shorebirds that we were discussing last class. The shorebirds have a little bit higher wing loading. It turns out that these flying vertebrates were quite sluggish and quite slow. And I found out that there's a lot of research going on in this subject recently. I found a couple of quotes that I wanted to share with you. One says that, well, first of all, these creatures were not birds. They were flying reptiles with a distinctly different skeletal structure. So they had a different sort of skeleton which allowed them to fly. Wing proportions and muscle mass. They would have achieved flight in a completely different way to birds and would have had a lower angle of attack to take off and initial flight trajectory. And in fact, there's some very recent results that propose that these guys didn't fly at all. They could not really stay aloft in an environment similar to the present, says Professor Sato from University of Tokyo. And there was a few articles that appeared in New Scientist and so on. And so there is indeed a little bit of a unknown here about whether these guys were able to fly or not. But very interesting question, Yasmin. Thanks very much. If you're interested, I've posted some links on Blackboard to the articles that I found. Okay? Okay, so then I would like to do an example that appeared in the exam of last spring 09. And I've printed out some copies of the actual page so that you can have a copy and we can develop this example together. Can you pass them to the back? Let's see if I printed 25, estimating that we'll do a full class, but let's see how that goes. All right, so here it is. You can read it. You can please write down the data. The ones that didn't get a copy, just write down the data on a sheet of paper and I wanted to give you a copy because there's some graphs, and so it's easier for you to try to read the graphs from, if you have your own piece of paper, rather than reading it from the projected image, but you can still see what we're going to do and follow it, okay? So we have an airplane that weighs 180 kilonewton and has a wing area of 160 square meters, a mean chord of 4 meters, and airfoil properties as shown. So you remember that we discussed last class the coefficient of lift, and we showed that this was usually presented in the form of a plot, and it had sort of this shape. We introduced the concept of stall, which appears when, as you can see in these plots, the coefficient of lift reaches a maximum, after which we encounter separation on the top surface of the airfoil, and the wing then stalls and lift is lost. So that is what's happening here. So you needed to remember, give me a second, Tim, to just finish the presentation. You needed to remember here from this question that it says here that the plane is designed to land at V0 equals 1.2 V stall. So you needed to remember what stall was, first of all. Yes, Tim?
What is chord?
Oh, the chord. So we introduced very briefly at the last class the basic nomenclature of airfoils, and it was just last class, so you probably haven't had time to go over it. But we introduced this nomenclature. The front of the airfoil is the leading edge, the back is the trailing edge, and we said the distance between these 2 points is the chord. That is the chord of an airfoil, and it's given there. And what else we have? So this it's basically this question is about remembering some of the basic terminology and concepts we introduced last class, and how to use a graph, how to use the graph of coefficient of lift. So I'll let you look at it and write down the data first, and then I'll clear up the annotations, the problem description, so we have a little bit of space to write on the slide. So I'll leave the plot on so that we can look at that. So, well, basically, first of all, we need some properties, the properties of air. We're going to just use the sea level properties at this point, because we're not told. Besides, and we are told that the interesting situation is landing. Of course, the plane can land at different altitudes, and the density might vary a little bit. But for the purposes of the problem, it's okay to just use sea level properties. And we have a density of 1.225 kilograms per cubic meter, obtained from some table. And let's see, what can we get? Immediately from the plot, we can see that it is also said in the question that the plane lands with a flap setting of 60 degrees. Remember that what the flap was? We also introduced that last class. The flap was this little part in the back of the airfoil. So we have an airfoil that sometimes has this little extra bit that can extend in the back, changing the curvature. And we said there are a variety of high lift devices like this one. This is a flap. The one that can be in the front was a slat, and they are used to change the lift characteristics of the airfoil. So first of all, we have that we have a flap setting at landing. Flap of 60 degrees. And therefore, that tells me that I need to use this curve over here. So far, so good? Right. At this point, we look at the maximum lift coefficient, which is over here. We kind of have to read from the plot. This is 1.6, this is 1.8. Halfway here would be 1.7. So let's just sort of approximate this to 1.75. Does that sound like more or less? We don't have much choice but to make an approximation. So maximum coefficient of lift equals to approximately 1.75 with flaps. Now we can read. So what is this position? This is the position of stall, correctly? Correct? That's when stall happens. And we were told in the problem that the velocity at landing was 1.2 the velocity at stall. So we look at what the stall conditions are first. Velocity v0 at landing is equal to 1.2 velocity at stall. And this is the stall point here. So what is now your question, Nathan, is the angle of attack. So now we read the same thing from the plot again. And we get, well, let's approximate it to 6, shall we? In the middle, sort of between 4 and 8. You agree? So the angle of attack is equal to 6 for the maximum coefficient of lift, after which the airplane stalls. So what is the stall velocity? What do we have? We have the weight, and if we imagine that the plane is approaching to land and we want at least the plane to not fall from the sky, so we want the lift to at least be equal to the weight. So we are going to use that the lift is equal to the weight, and the definition of the lift coefficient. If you recall, lift, let me put here, lift is equal to the coefficient of lift well, let me write it the other way around actually. I want a coefficient of lift, so I'm going to write coefficient of lift is equal to lift divided by 1/2 rho v squared times the area. And what we want from this is the velocity at stall. So we solve for velocity, and we get velocity is equal to square root of the lift over, well, basically 1/2 the CL takes that place of velocity there in our expression. And with L equals to W, we can get the stall velocity, speed. Please, you had a question? Yeah, exactly. If you recall, we said at one point, if the angle of attack is too big, basically what happens is the air is trying to go around the airfoil, but it is not able to follow this curved path because we have a very high angle of attack, and it separates and it forms a wake. And if you remember from actually we'll discuss wake a little bit more today, but we did introduce this idea of separation last class. And we said if there is separation, there will be this area of backflow here in the wake and a reduced pressure. So there is an increased drag and a reduced capacity to generate lift. And this is shown here very clearly in this plot where beyond stall, the coefficient of lift drastically falls. This is the behavior of all airfoils.
So then is it right to say that stalling and separation both depend not only on angle of attack, but also on speed?
Yes, it's correct. The angle of attack only varies a small amount. I mean, in normal maneuvers, right? You don't operate a plane so that, except for an acrobatic plane, you don't really operate it to extreme angles of attack. But at a given angle of attack, which in this case is quite moderate, just 6 degrees, if the velocity is very small, then we will lose basically the portions of air that are following around the curvature of the airfoil don't have enough inertia to follow this curved path, and they just separate. They run out of energy to continue here. Yeah. Another question, yes. At least, right? Lift has to be at least equal to weight. If we consider that momentarily in this situation that we're studying, there is no acceleration, but the plane is moving at a constant speed, then all the forces are in balance. The vertical force going upwards is lift, and the vertical force going downwards is the weight. They have to be balanced for there not to be an acceleration, right? All forces have to be in balance. And that's the reason why we make lift equal to weight. With this, we can now obtain the velocity, the stall velocity, because we have the coefficient of lift, we have the weight, we have everything. We have rho, we have the area. The area was given. Let's see. I'm going to take that 1/2 and put a 2 on the top. And we have the weight. It was 180 kilonewtons. So let's not forget our correct conversions there. A kilonewton means it's 180,000 newton. This is in newton. Let me just leave my units, carry my units. We know that's the way to do better in the exams, is to carry your units. So we want to do that. We have the density, 1.225 kilograms per cubic meter. And CL, we just got CL for just the stall conditions, is 1.75, stall conditions with flaps extended. And the area was given in the problem 160 square meters. In an exam, I would take the extra time to actually work my units out and see that everything makes sense, and what we have inside the square root should be meter square divided by second square. And the answer, 32.4. I have somebody with a calculator here helping me out. Very good. Meters per second. So what's the landing speed? 38.8? It's 1.2 times that, right? That's the first question. What is the landing speed? So we've answered the first question. Right? Okay. What's the second question? The second question is, what is the lift coefficient during landing? And so for that, we use the definition of lift coefficient, and we see that I can, if everything else is equal, rho is equal, lift is equal, and area is equal, I can do basically a relationship between CL and V squared. So we have, that's the only things that change, and so we have CL at landing will be equal to CL max divided by the V landing over V stall squared. And I get 1.22. So it's simply using the definition, the formula for CL.
Just out of curiosity, you know how like if you go down in the angle of attack, the lift coefficient decreases as well?
Yes?
So as it goes below 0, is it steady decrease even
Okay, you see that this point here has, let me see, 0.08, 0.04, this would be 0.2, is not completely 0, it seems. Okay, 0.2. So this means that the airfoil has some curvature such that at 0 angle of attack it's still generating some lift. If the airfoil was completely symmetrical, at 0 angle of attack the CL would be also 0. In this case, you see, of course, the effect of the high lift devices, the flaps, is to increase the coefficient of lift even at 0 angle of attack. The angle of attack being the angle between the chord and the relative wind.
Mike wants a trick plan.
Sorry?
I think Mike wants a trick plan. New barrel roll.
All right, let's move on. Okay. There we are. So we're going to discuss a little bit more about drag today. And I have put here the expression that we developed last class. We developed one similar for lift as well, but today we're going to concentrate on this one for drag. So we said also when we developed this expression that obviously to be able to do these integrations, we would have to know the pressure distributions and the distribution of shear, which is quite difficult, right? I mean, the only way that I can imagine to have that in detail would be to have a complete numerical simulation, a complete solution of the Navier-Stokes equations around a particular surface, and in addition to all the information about the surface, the angle, right? We need to know P at every point and tau at every point from a total solution, which we in general do not have. So most of the available results for drag on objects are obtained from experiments for this reason. The P pressure and wall shear stress distributions are known in general. So we use experimental results. So notice that we have two contributions to drag. A contribution which is due to pressure and a contribution which is due to the shear stress. So we actually distinguish between these two and give them different names, and this guy is called the pressure drag. And this one over here, guess what? The friction drag. Pressure drag is sometimes also called form drag because it depends on the shape of the object. So let's talk first about the friction drag or viscous drag. Pressure drag is also called the form drag. And the friction drag is also called viscous drag for obvious reasons. So let's discuss this first. Now let's recall our previous discussion first of the boundary layer. On a flat plate. So note that for a flat plate, in this expression here we have the angle. Remember we developed this for a unit area on an arbitrary surface. If it's a flat plate, then the theta is equal to 90 degrees because our angle was measured between the horizontal and the pressure. This was our theta. So if the surface is completely horizontal, the angle is 90 degrees. The pressure is vertical upwards, no, downwards. Okay? So 90 degrees. That means that if I put this back in the drag expression, what do we get? That the pressure drag is 0. And all drag is due to friction drag. So recall, and you can confirm this from our lecture 17, slide 9. We developed, we sort of sketched a solution for the boundary layer case. We didn't look at the details, but we explained how Blasius, a student of Prandtl, developed a solution, remember, by doing this a clever trick of changing variables and then turning the partial differential equations into ordinary differential equations, which he was able to solve. And I showed you some plots of what the boundary layer profile looks like, and we saw that all results could be obtained from that. In particular, we obtained for the Blasius solution a thickness of the boundary layer, and delta, the thickness of the boundary layer over x, was equal to 5 over square root of Reynolds, where Reynolds was measured with respect to the distance along the plate. Does this ring a bell? Boundary layer? Sort of, yes. I see. But you know that you did see it. Okay, that's good. And we also had a result for the wall shear stress, which was obtained numerically from the boundary, from the Blasius solution, 0.332 u to the power 3/2. U naught was the velocity of the free stream, and we had square root of rho mu over x. This was the Blasius solution for boundary layer over a flat plate. So now we can use this. Now recall that this applies only for laminar flow, though. Important. But we can use this to estimate the drag force of a laminar flow over a flat plate. So the friction drag is then, well, let's put a little f there to indicate friction drag, and it's just the integral of the wall shear stress dA. The angle is 90 degrees, so we know. And let's write the area. The wall shear stress, notice, depends on x. This was a two-dimensional flow, so let's just put a unit, a sort of a measure of the width of the plate for the area, and then we're going to have the integral of tau as a function of x dx. This is the width of the plate. So we can integrate this. Let's put in our expression for the wall shear stress. And we integrate between 0 and a length L, 0.332. I'm going to take the free stream velocity inside the square root first. I don't know, I did it this way. It's going to come out of the integral anyway. And basically we have the integral of square root of 1 over x. That's the only thing that matters. The rest is constant. So let's take everything outside that is not a function of x. 0.332, the width and square root of rho mu free stream velocity cubed inside the integral, and integral between 0 and L of square root of 1 over x. So just a little bit more work, almost done. Rho mu, and the integral here is 2 times the square root of x, and we evaluate between 0 and L. And I don't have space there to write my final solution. Maybe I'll make a little space here by erasing. I may change the color so that you can see the actual solution. I have a 2 here, so 0.664. Oh, it's not going to fit. Rho mu free stream velocity cubed. And L is also inside the integral, so it does fit, doesn't it? Yeah. But this is a little clumsy. Let's fix it. There. And remember, this is for laminar flow. So we actually have a measure of the drag, the friction drag for laminar flow. And so the next question is going to be, well, when can we apply this, and when does the laminar flow over a flat plate turn into turbulent? Transition occurs at a much larger Reynolds number than the case for pipe flow. Anybody remember the critical Reynolds number for pipe flow, more or less? 2,000. Very good. For boundary layer flow, it's about 500,000. So it's quite a bit higher. Okay? Let's see. I'm just going to... Well, I'll write it in the next slide. And let me see if anybody's still writing. And oh, look, I fit everything on one slide and I had extra space. Okay. So our critical Reynolds number for transition is, in the case of boundary layers over a flat plate, 500,000. Beyond that, we have turbulent flow. I probably have another slide for drag coefficient, don't I? Yeah. In the end, I made it fit. But let's do the drag coefficient here. We've just calculated the drag, so we can put it in the formula for drag coefficient. Right? This is going to be equal to 0.664, the width of the plate, square root of rho, mu, L, free stream velocity cubed. Is that it? Yep. Oh no. 1/2 rho. And the area of the plate is going to be W times L. The width times the length. Right? And then we have velocity, free stream velocity squared. So we can rearrange this a little bit, and we have 1.328 with this 1/2 here, and you see W cancels out, and if you put everything inside the integral, lo and behold, what do we have? What does that look like? Reynolds number, square root of Reynolds number. So it depends on 1/, right? So 1.328 over square root of Reynolds number. This is the drag coefficient for a laminar flat plate. Now, notice one thing. This whole development assumed that the flow was only on one side of the plate. If the flow goes on both sides of the plate, then you just have to multiply it by 2, the drag, right? For turbulent flow, there is no analytical solution, if you recall. There's nothing like that. But there are a a lot of empirical results that have been accumulated over time and have resulted in empirical relations. Let me just show you one, for example, that appears in the textbook, but there are others. So I'm going to, let's see, somebody's still writing over here. Done? Okay. Okay, so for turbulent, and just let me just write this and we'll have a little break. Write this expression, empirical expression for the turbulent boundary layer. We have no analytical solutions in this case. But plenty of experimental results. An empirical relation that is sometimes used, there are others. For the coefficient of drag is 0.031 over, not the square root, but Reynolds to the power 1/7. This is for the turbulent flat plate between Reynolds of 5 times 10 to the 5, and well, as I think this is just as much as the experiments are available, a Reynolds of 10 to the 7. If you want to look at the discussion about this on your textbook, this appears in the textbook by post on page 270. And this is for fully turbulent flow, but we could have a situation where we have a flat plate and the flow, the boundary layer is laminar. Of course, it's going to be laminar in the little bit at the front, right? And then at one point, because the Reynolds number is measured with respect to X going on top of the plate, so there's a bit of laminar flow in the beginning and then it turns turbulent. And so there's also a relation that is adjusted for the laminar bit at the front, and we'll do, when we come back from the break, an example using this expression, which is for mixed flow, where the upstream part of the boundary layer is laminar. And so we adjust then the coefficient of drag to the fact that you have a little bit of laminar flow and then turbulent, and you have the following expression, also empirical, of course, 0.031 over Reynolds to the power 1/7 minus 1440 divided by Reynolds. So let's have a little break now, and then we'll do an example using this boundary layer result.